Hello, Panther. Today I will show you something which I call the master equation. Have you ever been stuck when you have been computing, for example, this type of integral? So this video is for you. These types of integrals usually are computed using the answer is in terms of arcus tangent function or inverse tangent function. However, the method is quite complicated. Not so complicated, I would say, but rather cumbersome, because you have to this have to be rearranged, so it's some square, and you can make a lot of errors. For those of you who would like to learn another method which is dealing with actual formula, this video will be for you. So for this integral, for example, it's very easy to show that the answer of this particular example is 2 divided by square root of 7 arcus tangent 4x minus 1 divided by square root of 7. How did I... It's very easily plus some additional constant, integration constant. So you can see I have found the solution very quickly. And the quickness or the fastness of this solution is the key factor here. So I've used this formula. Q stands for any quadratic function which has the square of x, the biggest term, or the term with the highest power. This delta stands for discriminant, which is defined as b squared minus 4ac. Maybe you've computed a lot of times. So for this example, delta is minus 1 squared, which is 1, minus 4 times 2 times 1, which is 8, so it's minus 7. For the cases when discriminant is negative, you can use this formula. Otherwise, it can be used because there is, instead of this arc tangent, there is arc tangent hyperbolic and there is minus, or arcus cotangent hyperbolic. But nevertheless, for delta is smaller than 0, it's very easy. It's just arcus tangent, and this is the easiest and most common integral of them all for a negative delta. So this is the solution. So well, actually, if you take the derivative of this polynomial, you get 4x minus 1. So this is q. This stands for q prime stands for the derivative of q. X. So now let us prove this formula, because the proof is very simple. You just take the derivative of this integral formula. Oh, there should be also a c, but never mind. You take the derivative, and then from the definition of the integral, you have on this side 1 over qx is equal to 2 divided by square root of minus delta times the derivative of arcus tangent is 1 over 1 plus argument squared times the derivative of the argument, so it's 1 plus this squared, which is minus q prime divided by delta, because delta is negative, so this term is positive, squared, positive, and times derivative of this, which is q double prime x divided by square root of minus delta. So this can be simplified very easily, and you can simplify it, and this will eventually be, this is 2 times q prime double prime actually, so this is double prime x divided by this is minus delta is here, which is positive, times this is plus, so this is q prime squared of x minus delta. So this is it. It would be very nice is indeed true. So if this denominator is equal to 2 times q double prime times q, then the formula is proven immediately, because this will cancel out and we have 1 over q. So let us prove that q prime squared minus 2 is put on the other side of the equation, the minus 2 times q prime double prime times q is equal to delta. Let's prove this. This is generally a polynomial of linear polynomial squared. This is constant and this is polynomial. You can substitute in q is equal to ax²+bx+c, the general form of q polynomial, but there is a better way how to prove. It's taking the derivative, and if you do that you get 2 times q prime q double prime minus, and there is minus 2 times q triple prime q minus 2q double prime q prime. And this is equal to, if you take the derivative of left hand side, this is equal to left hand side is equal to this is also 0, because q is polynomial of second order, so the third derivative is 0. So this is 0. Since left derivative of left hand side is 0, that means that left hand side is indeed constant. We don't know this constant, but we can deduce this constant by substitution of x is equal to 0, because q at 0 from this expression is c, q prime 0 from this expression must be b, and q double prime of 0 from this expression must be 2a. So the left hand side from this and this, left hand side is therefore equal to q prime squared, which is b squared, minus 2 times q double prime at 0, which is times q at 0, which is c. So it's b squared minus 4ac, which is delta. So we have proven the formula. So this is indeed true, so it means that this must be true, because this must be 1 over q, so this is exactly the integral, our integral. Few examples of using this formula. If you remember it, it's good for you, I think. For example, this is very easy integral, and I will compute it very easily, because delta is here b squared, which is 1 minus 4, so delta is minus 3, so the answer is 2 over square root of minus delta, which is square root of 3, arcus tangent q prime, which is 2x plus 1 divided by square root of 3. How simple is that? And you can also try it for the special case, which as you all know, is equal to arcus tangent itself. Now you can use the formula and show it is indeed true, because here delta is just minus 4, because it's minus 4 ac and b is 0, so this is 2 square root of 4 arcus tangent. Derivative is 2x divided by square root of 4, which is indeed arcus tangent of x. So the formula holds also for this case. Let us compute, for example, another integral, but you know, it's not when you have this formula, everything is very easy. Let us compute this example. For this, the discriminant delta minus 4 times this, which is 16, so it's minus 15. So that means that the answer must be 2 over square root of 15. Arcus tangent derivative is 4x plus 1 divided by square root of 15. You can do any examples as you like, there are plenty of them. I think this is sufficient too, so you can do it yourself for any integration. It's very quick integration technique, so I hope you enjoyed it. This video on the master formula I'm using a lot actually myself, so I hope you will be also using it a lot, because it's the work now from this formula is very easy to do everything. So thank you very much, and Pantherei, goodbye from Ireland.